Maybe you should do at the beginning before everybody gets here, so that, because I didn't do it for other class, but I do it later on. Let's go over that problem. There is a question here that many people make mistake there, and actually, what page is it on? There is one example here as well in the here too as well. So let's go down here. I'll put it at here. Okay. You see, and this is the problem here, similar to what you are talking about. So let's talk about that while I have time in order to get that out of the way, since you are asking that question. So I have to find out my solution here somewhere. Okay, here it is. If determining the internal forces is very important, and people usually make mistake there. Let's look at this rod. You want to write it down, then that answers your question. Exactly. So here is actually one of the handout problem that I have given to you. So here is the rod, vertical rod here. Here is a support system. And then you have a 4 kilonewton load here. And then you have here a 12 kilonewton load applied. Let's say that point C. This is point D. And then there is another load applied here, 16 kilonewton at that point, which is point B. And let's say, of course, we are assuming these loads are at the center or on the side. It's 8 and 8, which makes it a centric loading. This load has to be at center of the rod. That's the first assumption. Otherwise, it will not be pure tension or pure compression. The load has to be at the center of the rod. So this load assumed to be at the center, or you can put 8 and 8 on the side like that to become 16, and 6 and 6 on the other side. Now, if I ask you, of course, this rod is under either tension or compression. If I ask you what is the force in this section internally, these are what you see here is, all I'm showing is the external load. This MB218 is about internal. So we want to determine the internal forces in section AB. What do you think the internal force in section AB is? Compression. Compression? How much?
16.
16? Compression? Wrong. Absolutely wrong. Yeah. Now, what you are saying is under this scenario. If I have a rod here and I have 16 on top of that, yes, this is under 16. Is this the case? That's exactly what she's asking. This question is very, very important. Without recognizing this question, you cannot go to the more complex problem which we have at the end of the chapter. So please pay attention to that. You just don't, because this is several sections of the rod, and the upper part is going to have effect on the bottom. So you cannot suddenly say 16 here. So what do you say about here? The way you're analyzing is use your logic for here. Then what is the force here? 16 minus 12. That means you are using this free body diagram. Is this correct, free body diagram? You see that? So that logic doesn't work here. Is that a totally wrong assumption, because you are looking at the external load and you are determining only based on segment by segment, but these are attached to other part. Yes or no? That attachment changes this. So the way we should do it, exactly what I said to do in class, that's what we do that. So let's start either from top or bottom. Doesn't make any difference. Let's start at the top and make it here, because the top is easier, so later on you can change it, go from the bottom. If you want to go for the bottom, first thing you have to do, you have to find a reaction there. Okay, let's find a reaction. How much reaction do I have here? This is 16 going down. This is 12 going up. This is 4. What should be put here? 8. Going up or down? Up. Okay, fine. You see? So as you see, that assumption that you use now, you said 16 at the beginning, remember, that's wrong. So as you see, and I cannot use, and this is what, interestingly enough, some students do that. They take this part and say 16 minus 8, that's 8. That's not what we are talking about. Let's just start from top or at the bottom. I'm going to start from top. It is easier. So you need this free body diagram. This is the 4 kilonewton. Yes or no? What's the force here? That's very simple. That you should be after. That must be 4. Yes or no? Correct? So I'm going to internal force. That's only the section above that cut. Everybody understand that? So I have a upper part or the lower part to worry about. I need a color. So I'm going to that. So I'm putting my internal force in color. So here I have to cut. This is my cut AA. Everybody see that? So I have this part or all of this to be considered. Yes or no? Therefore, here I need to put here a 4 kilonewton like that. This is so simple. Now, what is member CD on there? Member CD is on there. 4. See, this is it. This is 4 kilonewton under compression. So write it down here. So I'm going to that. CD, force in CD equal to 4 kilonewton in compression. Now we want to calculate BC. Yes, sir. So I have to make a cut somewhere between B and C. Not at B, not at C. Somewhere between B to C. Actually, if you go to B and C, you get invalid answers. So I'll show that to you at the end. Now, I don't care about C or B. I want to see what happened to this rod. Everybody understand that? That rod is from here to here. Yes? So I cut a cut here. This is cut BB. Now I have to worry about the upper part or the lower part. All your question going to be answered here. So now I have this time I have a free body like this. Let's go to BB. So this is BB now. Now how much force do I have here? 4 kilonewton. How much force do I have here? Is 12. So what should be my internal force here statically? The balance, yes? How much is the balance? 8. Is it going up or down? Down. Therefore, it is in tension. It's pulling it. Is that correct or not? Look, something you never see it from here. Everybody understand? You don't see it with the external. You have to go through the idea to cut the item at certain point, determining what kind of internal forces versus external. What you were doing all wrong at the beginning, which I put this question purposely on the handout to show it to you, but I was going to show it later. So I'm glad that you mentioned that. So therefore, as you see here, the member here is under 8 kilonewton. Therefore, it's pulling it down. Therefore, that portion of the rod is under tension. Yes or no? Therefore, force in member CB or BC is equal to 8 kilonewton is under tension. And so on and so forth. Of course, the last part, I can show either the upper part or I can show the lower part. Both is easy. So instead of easier, I go to the lower part. Everybody see that? So I show the lower part. Now right away, everybody can see the answer, what the answer is. If I show the lower part for this CC, this is cut CC. So therefore, I show like this. Here, I have to remove this, by the way. So we remove here. Here is the 8 kilonewton. Obviously, this part is under what? 8 kilonewton. Under 8 kilonewton of compression, not 16, as you said it at the beginning. Yes or no? Correct? Now, 16. So F AB is equal to 8 kilonewton in compression. Now, you want to see another version of that, which is going to help you draw your forces in positive and negative format, which gives you exactly like that. You start from top, like this. So doesn't matter, one side positive, one side negative. You start in, let's say this is negative, and that is positive. How much force do I have at point T? Minus 4. Yes or no? Correct? I have minus 4, minus 4, minus 4. When I reach to point C, suddenly I am adding how much? 12. So from minus 4, I have to go to plus 8. So this is minus 4. So go from here. I have to go to plus 8. Then you continue to point B. As point E, suddenly you adding negative 16. Yes or no? Correct? So therefore, you go like this, negative 16 from plus 8, you end up with minus 8. Notice, if you are at C or at B, nothing shows there. You have to be an epsilon above or epsilon below. Everybody understand what happened? An epsilon below, what's the force? The force is member here. Yes or no? The force is minus 4. For member CB, the force is plus 8. For the member AB, the force is here. You just have to stay an epsilon above and below this point. Everybody understand? In order to get at that point, nothing shows because they are connected to each other. Yes? So you just go by the cut, which is easier, or go by this graph. So what I'm saying that actually if you go to point C, it is ambiguous. That doesn't show anything. You have to stay epsilon above. You are in member CD. Yes or no? If you go an epsilon below, you are on member CB. The answer is totally different. Everybody on every part of this structure are doing, is not like one rod under one tension or one compression, which we were talking before. Is that understood? Yes? Everybody got this idea? Yeah? Okay, good. So let's now proceed. So that was, of course, one of the questions which I was going to answer it later on, but since you asked, I brought it forward a little. Now let's go back, talk about simpler problem than this, which is pure tension or pure compression. Let's go back to that example that I showed you before. Again, I have to show that for the sake of video. I should go back. What page was that example that we did? Yes, it is page 6, I guess. I have to go. This example. Okay. On this example, we find out all the internal forces. Yes or no? Correct. Now here is the rest of discussion, which is purely now strength of material. What force did we find for this member? You have it there. It shows there. 333 pounds in compression. Yes? Okay. This is the idea now. We are going to talk about normal stresses and shear stresses. Today's lecture is about this, which is the two types of stress that you always going to have encounter in every problem from now on. One is normal stress, one is shear stress. Okay, in member CD, this is what we got there. In member BC or CD, I forgot what it was. In member DC, okay. In member DC, we end up that having a force of 333 pounds here, and this is at the center of the rod, so we call it axially loaded member. So this load should be exactly at the centroid of the rod. If it is not, then it creates a moment. We talk about that later on. Is that understood? Yes? Now, what happened here, these two loads are external load. This is a two-force member, so purely under tension, I'm sorry, I put here in tension. Actually, the result of our example was not in tension. It was in compression, as I recall. Yes or no? Correct? Double check it. I have to double check that. That was 333 pounds in compression, as I recall. Yes, this was compressing. Is that correct or not? Yeah? So it is in this format, which is doesn't matter for the sake of discussion, that this rod could be under pure tension or pure compression. In this example, it was good. Now, we call this force P, which is external force. So that's how the lecture in your book being explained when you go through your reading your book. And then you make a cut here, yes, somewhere, so find out what's going on in that. Then you draw the free body diagram either of the lower size or the upper size. This is the external load of 333 pounds. Statically, we are going to show here one force representing the internal force as we did it last time. And I'm going to do the same thing here. And that force was force N. Normal force. Why do we call it normal force? One more time. Because it is perpendicular to the cross section. That's why we call it normal force. Okay. And then The value of the normal force here, everybody can see it is so simple. First of all, notice this has nothing to do with the sign of this tension and compression, has nothing to do with the sign of these forces. These forces has X component and Y component. This has X component plus one. This, we call this in compression, and it is compression, we call it negative. Everybody understand that? So therefore, what happened here, that's the discussion we want to have. Let's say that this was a rod similar to what I have here, but this is a hollow. Let's say it was solid, yes or no. Therefore, it is a solid rod like this, and you have a 333 pound force here. You are going to have, if this is sufficiently further from this cross section, you have here a uniformly distributed push, like a pressure, pulling it because you were pushing it that way to crush it, yes? Which is uniformly distributed. These two are the same. This must be, the sum of this must be equal to that, yes or no? This uniformly distributed forces applied to this area, we call it sigma or normal stress. So that is what showing the sigma is always very difficult, for we always symbolically show it with the n. As soon as you see from now, you see the n, you are will deciding that is going to create a stress. We call it normal stress in the compression mode. How do we calculate sigma? I'm going to put it here. So this is what happened there. If the area here, if this is the area of A of that crosser, whatever that area is, the area could change from object to object. Obviously, everybody knows from simplest static that sigma multiplied that this area must be equal to n, yes or no? Because this is a uniformly, this is high school question. Uniformly, this like a wind pressure over this board. You just multiply the wind pressure by the area, yes or no? This is a pressure. Multiply this sigma by area must be equal to the force, yes or no? Therefore, start like that. You take the sigma, you multiply that by the area, that must be equal to the N or normal force, or sigma equal to force over the area, of course, normal force over the area, which become equal to N over the A. Notice in the book, they call it P over A, which in this case, N equal to the P. I don't use that because if there are several forces here, I have like here. What you see that? N internal has nothing to do with the external. I have to find here. The internal here was, these are the N. Everybody understand what I'm talking about? This is the resultant N for each segment, correct? Therefore, that's why I don't like to use it P over A, because that gives you a wrong impression. So I put instead of that N over A. And of course, in general, it has a sign as well. Sometimes it is tension, sometimes it is compression. Then I give you the size, you can calculate that. This is the idea of a normal stress uniformly distributed over the cross section. What would be the unit of that? Sitting right in front of the force over area. So what's the unit will be? Pound over inch square, which usually we call it PSI. So learn this one, because this is engineering work. This is what you see in the book, but this is the more, I want you to use that one. When you go to put air in your tire, how many PSI? Remember PSI, 30 PSI, 30, that's 30, you are putting 35 pound per square inch inside your tire. If that you go to 40, you are more pressure, you are bound to break it. Is that correct or not? Everybody see what I'm talking about? That is the PSI, pound per inch square. That's the unit we are going to use. I'm going to use always PSI. You can use this, but I do not recommend it. Get used to it. Of course, there is PSI. If it is too small, we use KSI. What is KSI? A kilo. Well, it is 1,000. Write it down. Equal to 1,000 PSI. So this is the unit in our system. Yes. Doesn't matter whether it's tension or it is in compression. Now, in the metric system, what will be the unit? Please pay attention. In metric system, what will be the unit? Again, what is the unit of force? Is Newton. What's the unit of area? Is not millimeter, meter square. Is that correct? So that we call it Pascal. Pascal is equal to Newton over meter square. So we can change that to that system. And then, of course, the unit will be in Pascal or kilopascal, because Pascal usually is very small. Newton is much smaller than pound. Everybody knows that. Meter square is much, much larger than inch square. Then naturally, Pascal is very small. We never express things in Pascal. We always use kilopascal or megapascal. For wood and material like that, which is medium strength, we use kilopascal. For metal, steel, we always use megapascal. You will see later on, I keep using that again and again. So generally, stick to these two units, kilopascal and, which is kilonewton per meter square. So that's the unit that you are able. Now, this was the normal stress, could be tension or compression. Now let's, on the other side, let's talk about the shear stress, see what happened there. There are always two types of stress, either normal or shear, and nothing else is there in the rest of your life. So no matter what you are designing in future, whether it's a piece of the shuttle going that complex problem, it still is normal stress and shear stress. There is nothing else, believe me. However, it's simply said that there are thousands and thousands and thousands of classes you can go to get to that point. Everybody understand what I'm saying? It's not that simple. However, let's look at the basic, which is the something to be shear off like a scissor. So this time I'm going to use my item similar to this. Rod again, as we had it before. Again, cross section doesn't matter. This time I'm going to apply two loads like this, P and P here, which are very close to each other, an epsilon separation, like a scissor. When you have a scissor, notice there are an epsilon, they are not right on top of each other, otherwise you don't have a scissor. They're touching each other, but goes like that, yes? So these two P are like that, so one is going down, one is going up, which is in equilibrium. However, I can now, because there is an epsilon between the two, I can make a cut here between the two and study the equilibrium of the left-hand side or the right-hand side. This time, when I show it like that, mathematically, this is what's going to happen. This is the left-hand side. I have here a force P. So statics tell me I should have here a force in the body. Notice, these external forces are not in the body of material. I want you to again re-emphasize this point that I have seen people make mistakes. People go through the entire ME 218s. I have seen this happen a lot. And then when I ask them, when they come to 219 or for other reason, they come to me, I said, they cannot distinguish between the two because they think P is P, N is N. That's totally different. Static is all about the external forces, those P, that everything we talk about. Now we are going inside the body and find out how this body is going to behave because of those actions. Everybody, those behavior, first of all, is going to be explained in form of sigma, and then more stuff coming after that. Is that understood? Yes, how it's going to behave, how it's going to deform, etc., etc. Now, statics tell me again, like before, I should have here a force in the section, yes or no? That force in the section is not normal to the section. It is in the section, then we call it shear force. Remember that? We talked about it last time. So let's call it, is that correct or not? Yeah. Again, statics tell me these two are equal. Again, this is imaginary. Nothing, there is no shear here equal to that. What is inside the body, because you are trying to cut the body, it is a uniformly distributed stress there, yes or no? So if I show that in the 3D scenario, let's say this was a rectangular cross section. So you have a P here applied, and then you have here stresses. I'm assuming the stresses, again, like last time, uniformly distributed. So you have here stresses not perpendicular to the cross section. In the cross section, uniformly all over the place. Unit are all the same per unit of area. So here is this. That is the, we call it shear stress. This time we show that with tau. I'm going to go back, show it there. So therefore, this is the tau. Let's put it here, and this is the area. Now again, if I multiply tau by A, I should get the P. Is that correct? Because the shear force must be equal to P, correct? Look at here, statically. P, shear equal to P. The sum of this must be equal to P. Yes, correct or not? But this is the real one. this is how we symbolically represent it. Everybody understand? This is what's happening in the body. There is no forces in the body except stresses in this format. Yes? So tau equal to, now again, we write here tau multiplied by A, because this is uniformly distributed. Let's say tau is 50 and the area is 10 square inch, so you multiply that to get the value of the force, and that value of the force is either V force, which in this case equal to P. So let's do it this way. But in general, that what you see in the book, they're always using P for the format. I'm going to change that to the V again. So I'm going to put that formula here because we need that formula there. So this was normal stresses, and this was the unit. And now we have, and there is a sign, plus or minus. Tau also has a plus minus, but I do not worry about it for time being. I will explain that in a week or two when we go to the general stress. Then I show you how this sign works. For time being, you just come with the magnitude. It is okay for your homework. Anytime there is asking for the shear value, don't worry about sign of it until I explain it to you. The sign become important later on when we get a little bit more advanced. However, tau also become force over area, but not normal force. I'm talking about shear force. Therefore, equal to the shear force, that's right, over the area. And of course, the way presented in the book, they say P over A, but I would rather write it shear force over A because this is internal. Usually we use the P for external. So I want you to see the difference between the two. And of course, the unit, there is a plus or minus there. Discuss it later. Of course, the unit will be exactly the same because the unit is force over area. Doesn't matter. Units exactly the same. Is that understood? Yes? Now, knowing that there are only two types of stresses and nothing else, now we can have some simple structure put together and study that. Okay? So this is what I'm going to do for the first example of engineering work that you are encountering in your life. And that's the beginning of it. Yes? So let's make a structure here. Let's say that we have here one piece of wood here, and I want to connect this piece of wood together. So I put here, both of them have the same dimension, the same thickness. And I'm pulling this with the force of P in general. Now let's give it a number just to 1200 Newton. Of course, I have to put here P equal to 1200 Newton. If I'm putting these two pieces of the wood together like this, and I want to connect this together, guys, I can do it this way, which is very weak connection. Everybody understand? I can put these two wood together and put a glue here, yes or no? Or I can put here together and glue it, yes or no? So these two are now work at one piece. Is that correct or not? This is the simplest assembly that we can find. Let's say that this overlapping is B. The thickness of the plate are T for both of them. And if I'm showing that three-dimensionally, which we need to do that, okay, this width of the plate, W, is width of the plate. For this example, I'm going to put all the number there. Let's assume that W, or the width of this plate, going depth of the plate, is equal to 200 millimeter. Let's say the overlapping of the two wood is equal to 100 millimeter. And let's say the thickness of the wood each are 25 millimeter. Both wood are the same. Yes, like here. Yes? And we have glued this together. Correct? First of all, what are the two pieces of wood on there? If I'm pulling this one and pulling this one, the wood is under tension or under compression, or is it under shear stress or under normal stress? You're pulling it under normal stress, yes? If you're pulling it this way and I'm pulling it this way and I cut it here, it's under normal stress. I'm not talking about the glue. So maybe I should talk about glue first. So you are thinking about glue. That's why you were thinking. Let's go back to the glue because I glued this stuff. The glue is under normal. I mean, the glue will be shear, yes or no? You are putting it this way, yes? So this is the free body diagram of the glue. So if I'm, actually I can use now that. This is the overlapping. So let's do the lower part because that's easier. So if this is piece of wood, I'm showing the lower part now. Here is the lower part, which is like this. Sorry for this picture, it's not great, but that's okay. That shows you the idea here. Okay, so this is the overlapping area. Is that correct or not? Yes? This is 100 millimeter by 200. Now what happened here is this. You have 1200 Newton force here. You should have in this, because we have separate this at this level, we have separate this lower part versus upper part. Therefore, I should have here a shear force going this way equal to 1200 Newton as well. This is so simple. You don't have to even think about it twice. I'm just showing it just for you to have all the detail. Of course, this is going to be uniformly distributed over the entire, this is symbolic representation of that. Again, remember, that's what we said. In general, these are stresses going this way. Is that correct or not? That's shear stresses. So what's the value of tau? Let's calculate that. What's the value of the tau on the glue now? This is what we are doing that. What kind of glue, in other words, do I need there? So the tau on the glue, tau equal to the force over area. What force did we have? Because I already did put it over there. Remember I explained that. The force is 1200 Newton. What area are we talking about? Area of the glue, yes? Not one side, not both sides. Both sides are the same because they are glued together. So therefore it would be, this is B and this is W. Is that correct or not? Yes, so it is 0.100. We do it in meter because we need Newton meter. And then 0.200 because this was 100 millimeter by 200 millimeter. So you just subtract, this becomes 60,000 Newton per meter square, which is Pascal, which, as I said it earlier, we show it with 60 kilo Pascal. So the shear stress in this glue must be reaches to maximum. So if I have a glue that doesn't reach to that level, which usually the case, I cannot glue this together, but we'll discuss that in a minute. However, the board itself is under tension because you are pulling it, yes or what area do I have to use to calculate sigma? So this was tau, you can put it here, glue. Now sigma on the wood, so let's put it this way. So that means you have to cut it here, yes or no? Exactly what I did over there, yes, to cut it. And what area resisting that tension? Look, it's sitting here, tension or compression, this area, yes? So what area are we talking about? Number wise, again, the formula is there. Sigma equal to force over area, the normal force. You have to do this again and again, but it is so simple. Here, what we are talking about. Here is the wood. This is the external 1200. This is the internal. I don't have to show that because this is so. And this is going to be uniformly distributed over cross section. What cross section are we talking about? This is the cross section, yes or no? Yes? So this wood, the cross section of that wood, like the cross section of that rod, or cross section here. Everybody see that? Yes? So that's the piece of wood. This is the resistant force. I'm pulling this board like this. It is under tension. Yes or no? What area are talking? Exactly what you see. It's in face of that wood which is facing you. Is that correct or not? Yes? So therefore sigma become equal to, sigma in the wood become equal to 1200 Newton divided by this area, which is the same everywhere. This section, this section, this section, this section. Actually, that equal to how much was it? The 200 was the width, and times the thickness, which is 0.025. So you calculate this together. So therefore, that become 240,000 Pascal equal to 240 kilopascal. And it is plus because it is in the tension mode. Yes? Okay. This was your first assembly. Now we are going to change that a little bit too. Correct? Now, let's say I cannot find a glue that goes up to 60, how much did we come out? 60 kilopascal. There is not such a glue there. Of course, glue comes different type of glue. You have super glue, you have cheaper glue, you have the industrial glue, which is totally different. They are much stronger. But it goes to a certain level. It stops there. So if the glue doesn't do the job, what should I do? And this is wood. Remember, if it was steel, I could weld it together. That's it, or put it together. But another choice is to either nail it or bolt it together. Yes?
Couldn't you just increase the area?
What?
Couldn't you just increase the area?
Oh, of course, yes. Then, of course, you can do. In order, yeah, good question. Again, good answer. But I'm just trying to show you another part of a structure. Yes, she said quite correctly that if this is too much for my glue, I can increase this B. Everybody understand that. So I have more B there. I have more glue area, so stress becomes less, obviously. But I'm trying to teach you other alternative of the system to find out what's going on. Yes? Mm-hmm. Let's say that instead of glue, we decide to bolt it together, a metal bolt, which is here, like this. Is that correct or not? Everybody see that this is the bolt? Yes? Yeah. So what do I have to do in order to put a bolt there? I have to drill a hole in the wood. So that is the scenario here. Let's say that. Of course, your option is also valid. Don't get me wrong. But this is lecture, so I'm trying to show you that. So I'm going to erase now this time. This number you should remember. You have it there because I have limited board here. This time we are drilling a hole like this into that and dropping a bolt there. So the top of the bolt will be there, and then you, of course, you put the nut here and you tie the nut there, etc., etc. The picture there is there. So what you see on the top is this again. On the top or bottom this time, you see this scenario, and then there is a hole there, and let's say the diameter of this hole is given equal to the D, because depend what kind of the bolt you want to use there. Yes? Okay, first of all, my material suddenly went from this cross section, guys, everybody understand that, to this cross section. Not exactly like that. This is a very worst design. Suddenly there is a hole there. Where should I calculate? If somebody asked me find the sigma in the wood, where should I check my sigma? Should I check it like before when I did it there, or check it where the hole is? Where the hole is, I have less material. Everybody understand it already. I'm making weaker in that spot. Everybody see what I'm talking about? You went from this cross section, if I cut it here, to this cross section. The hole cut the section into, you see what happened here. So in other words, I'm going to explain it to you. If I'm here, nothing there, but I am at this level, I have this cross section. Yes or no? So if I show you that three-dimensionally, you have this. You have a hole there, you have this going down, like this is the thickness, this is the thickness. So this is how it looks like. Is that correct or not? Yes? So you have less material there. So this time, sigma, because of the hole and because it is in tension, when it is in compression, that's a different scenario. I will explain that to you next time. However, when it is in tension and there is a hole there, there is a separation between bolt and the wood, and therefore I have to subtract the area of that I see there. Is that correct or not? So that my cross section is not the full cross section. My cross section, which is resisting my normal force, is that much material. Yes? So this was 200. Now I have to subtract from it the diameter of the hole, of course. Therefore, sigma becomes the force. This time, let me put it in general, then I put number there. So I put the force, which is the normal force, divided by area. The area here becomes W minus D, because this was W minus D, which is this 2, multiplied by thickness. So that's the thickness remained the same. For our problem, that was 1200, and then W was 0.2 minus diameter was, I did not give you the diameter. Let's say that we are using now a bolt with a diameter of 20 millimeter, just for the purpose of the discussion. So the bolt has a diameter of 20 millimeter. So that become 200 minus 20, or 180, which is represented here, 0.02, which is 180 millimeter. Multiplied by thickness. Thickness was 0.025, so we had that. when you calculate this sigma, which is still is plus because it still is in tension. Of course, it is weaker in that cross section. Here is a solid cross section. Here is a hole there in it. So therefore, the sigma become larger. It becomes 260. I have to look at my notes. Somebody you can calculate, check it. I guess again, the number doesn't matter. We can always correct that later on. I think it become 267 or 64. I don't remember. Oh, I had it here. 267. Okay, 267 kilopascal. Of course, remember what kilopascal is. 1,000 is there. So that means the stresses is, you always calculate the stresses at the weakest spot of the structure, not in the stronger. Yes? Okay, that's one question we answered now. Notice the sigma previously, solid versus this hole, yes or no? Now, what is the bolt under? What's happening to the bolt? If I'm putting a bolt between the two, and look at this structurally. This is here is the system like that. Here is the two plate. There is let's assume there is a nail there or a bolt there, in this case a nail because it's a simpler structure, and you are pulling it. What's going to happen to is going to shear off between two plates. Is that correct? So exactly that's what you have to apply it here. So the next is in this structure, I have to calculate the shear stresses in the nail. So therefore, this is what you do. You either show the free body diagram of the upper part or the lower part for the first. But you, as I said, this is the first lecture. After that, you can do whatever you like. Choice is yours. This is 1200 pull, external. Then there is the bolt here. We are assuming that bolt here being where the glue was. Now see, the bolt does exactly what glue was doing. Everybody understand that. So therefore, this is the nut still is there, sitting there. But here you have cut it there. So what you have on top, you have it here, a force going in this direction, shear force, which should be equal to 1200 Newton as well, which is uniformly distributed on the cross section of the bolt, yes or no? Which has become a shear stress. So therefore, here we go. So tau in the bolt become equal to the force, 1200 Newton. Notice this is equal to that shear force divided by area of the bolt. Area of the bolt is the pi times the radius squared. Radius is 0.010 to the power of 2 in meter format. And if you calculate that one, the calculation ends up to be 3.82, I believe, 3.82 megapascal. Because this is much smaller number. Of course, this is metal, so this is 382 megapascal. Notice when it was in the wood, I was expressing it in kilopascal. This is the metal. Bolts are usually a higher strength still, so therefore is much larger. Is that correct or not? Yes? Sometimes we do things a little bit differently while we are at it. Let's explain all of that. Then we are going to have sometimes, because of this assembly, instead of that, we have this kind of assembly. You have seen it in some of your machine connection. If you want to haul, let's say, a tractor with your car, there is a little, you put a little of the little hook there behind on the back of your car to pull it. We call it like that. It happened like this. So you have two pieces, one going like this, and two pieces going like that. Everybody understand that? So there are two pieces rather than one holding the middle one. So you are pulling this one with the force P. So of course here you cannot have P and P. Here you must have P over 2 and P over 2 to make it in equilibrium. So if you put through a bolt here, this bolt is going to be cut in two areas. So instead of single shear, we call that one single shear. We call the other one a double shear scenario. So please write it down. This was in single shear action. But here, as you can see it easily, I don't have to show it to you. If I show the free body diagram, I can show the free body diagram of the middle part, or I can show the free body diagram of the top part, both of them saying the same thing. If I show the free body diagram of top part, this is P over 2. Obviously, this is the bolt, and here is the cut, and the shear force here will be P over 2. Is that correct or not? Yes. So actually, shear stress become half. Yes, so we call it double shear. So tau, this time become P over 2 over the area. Or you have another option to show the middle part. The middle part is here is P, but the bolt here is here, but it's been cut here and cut there. Everybody see that? So therefore, you have here again P over 2 and P over 2, which is the same thing that you have two area, but you have two area here being cut, so tau become equal to P divided by 2 area. As you see mathematically, that's the same. So it doesn't matter whether you see the free body diagram of middle part or the free body diagram of upper part or the lower part. All of them end up, all you have to do, make the load double or make the area twice. Either of them, not both of them. Is that understood? Yes? Correct? Now let's talk about one more thing before I go to the handout and show you all the handout the scenario there. So, and that is the following. Let's assume this is a solid steel rod, okay? If I push it on this wood and press it down, does it make a dent here? Yes or no? No, if I push it hard. You are saying no. If I push it hard enough, it makes a dent here. This is normal stress or shear stress on the wood. What I'm creating it. Normal stress. However, this is a little bit different from this stress because this is the stress between two different material. We call it bearing stress. So please write it down. Although it's normal stress, your guess was absolutely correct. So the one of the variation of that one, so I'm going to put here in front, is the bearing stress when two different material touching against each other. Yes, I put this wood, let's say this is solid wood, against here. This is different type of wood. If I press it down here, there is a normal force between the two. Is that correct? Or that force become uniformly distributed? Yes? So therefore, sigma, we call it bearing. So sigma bearing, or you can show it with B, is equal to, again, force over the area, but you have to determine what force and what area depends on the scenario here. So for example, if I have here a bolt here and I'm pushing it down here, notice this washer here, is there washer there? Yes or no? Do you think that washer is touching the plastic when I'm pulling it down? Is there something going on between the two? So where is the bearing area? The bearing area is the washer, the area of washer with a hole at the middle. Everybody understand that? That you have to determine. Now, your job from now on, I explained all the basic. I gave you at least 10 or 12 different problems. You have to look for this normal stress and bearing, shear stress, etc. Each problem has its own merit. Some of you, I'm sure, will do your own job, which you will be okay. Some of you will not get it. So the first thing you do, you go and open the solution. Then we are in trouble, guys. So that's where the trouble starts. The more you practice, the better you got that. And that is the key. The rest of it will not come to you. Every engineering problem I can give you based on this simple material, I can give you 10,000 different problems. All of them look different from each other. Your job is to look into it to see where is the shear stresses, where are they, what cross section, what angle. This is all depends on your static first. Second, in this little information here, everybody understand that there are lots of problems. Basically, I am done to the end of this end of your set of homework. You should this weekend you should be doing all your homework. But now let's go to this handout. This was your problem. Then let's go a little bit further up. Go to page 4 here, to page 4, guys. This is very important. This is what I was talking last time and today about the internal versus external, which this is right out of your static book by. This, if your static book that you were using last quarter, this, remember we skipped chapter 7? And if, yes, we did. And I asked, in my class, I asked my student to read these few pages. They probably didn't. So that's okay too. Everybody, I asked you if you want to prepare yourself for ME 218. Some of you may recall if you were in my static class. I said read the 4 or 5 pages of chapter 7 to get ready for the internal versus external. Because static is all external. Strength is all about internal. Now look, we have a beam here. Look, we discussed this one totally. Of course, you have 2 sections here, right-hand side, left-hand side, everybody knows. Notice there is a normal force, there is a shear force, there is a moment. Right now, we are only on the normal forces and shear forces, not the moment. Moment will be in chapter 4. I said it before. Torsion will be in chapter 3, which 2 weeks, 3 weeks from now. Is that understood? Yes? Now go to the next page. That's very important for me because you have also a 3D problem. This one is very important for you to recognize the difference between 2D and 3D. You have your handout, look at it because this picture is not perhaps not too clear. However, look, here there is a force here and each force has 3 components. This is internal forces, not external forces. If I find the internal force there, each force will have 3 components. Yes? Look at that. There is Fx, Fy, and Fz. Which one is normal force? Y is the picture there. Look at your, the Y is, I purposely changed the X to Y in order for you give me the right answer. The Y is the picture that you have there. Y is normal force. The other 2 components of the force are shear forces. Everybody see that? This is what we are talking about. So if this is like that, doesn't matter where it is. I don't care. This is normal force. This is shear force. Then you have one M here, one vector M. That vector M has 3 components, Mx, My, and Mz. One of them is not normal anymore. We don't call it normal. Look at the picture. One is this action. I'll show you to you. This is torsion. The other 2 are bending. These are the discussion we are going to have in next few weeks. Everybody understand what happened to this object. However, write it down if you want to write it down. Out internally, when we have a force, internally, when we have a force, one component will be normal force, the other 2 will be shear forces. Just what you just, we just said it, let's write it down that in order for you not to go. So out of all the forces that go inside the body, you have the force like that, has 3 components. One become normal force, the other 2 become shear forces. Out of 3 components of the moment, one is torsion, yes. The other 2 are bending. So in one of your homework that I have given, you have to determine it. You don't have to call it torsion and bending right now. You can call it like a static, calculate Bx, By, Bz, or whatever. But you understand that that's what we are going to do in future, yes? Now let's go over next few pages, see what we have there after that. After that, we are going to have, well, here is the example we did, started Tuesday, finish it today. This is another example here. This time has a, instead of uniform load, has a rectangular load. Everybody understand? I left that up to you. There is one solution here. If you want to study a little bit more and you do it yourself, then you check here. Don't try to duplicate this or look at it. By looking at it, you don't learn. Just cover the solution and then do it yourself. If your answer is correct, then go to your homework. Everybody understand that. That's all trying to help you in this format. Then we go here, page 8. Everybody should be on page 8. That's what we were talking about all today. This is the summary of what we did today. Look at it. This is an object under tension. This is how we show it. Picture B and C is how we symbolically showing it. But in actuality, it's like that. Everybody see the sigma there? Yes? This is the normal stress, correct? Yes? But we don't show this ever from now on. Everybody, we always show it with the static equivalent. Yes or no? There is the internal and there is the external and internal. Everybody see that? Now, the next object is an example like what I did here. There is a rod like that, cut differently. Obviously, this area 1 and this area 2 are different. This object is going to break at area 2. Yes or no? Because that's where the stress is less. Is that because the stress is larger? I'm sorry. The area is less, the stress is higher, as you see it there in example. Is that correct? Then, of course, from the formula, the larger the area, the less stress. The lower the area, the more stress. Is that understood? Yes? Then go to the next page. This is just for you to review in case you did not grab all the ideas there. This is a connection of the bolt system. Do you see that? Yes. And the shear, I'm showing the shear there. Everybody see there? Of course, this is the single shear, correct? The unities are there. This is a double shear, yes or no? This I have not covered. I'll mention that later on. Just keep that with you until I finish this one, because this is one kind of bearing, but I have to bypass that for time being until next time. Then go to the next page. These are the actual picture. Look at this. This is what you go outside, see in that building they are building. You will see that. This is a column. This is a rod under tension being connected with a pin. Everybody see that? The rod is under tension. This is actual pin, almost damaged because of shear. Everybody see that pin, what's happening to that pin? Yes? It's trying to shear off here. Yeah. That's when they say go to inspection on the bridges or in the freeways or whatever building. When they see this, immediately they stop traffic and say, well, let's change this one, this part. Is that understood? Yes, or support it for some, because this is about to go, right? Because of the fatigue or because of being rust or etc. This is a double shear, yes or no? Okay, this one, let's go talk about it. This one, now look what happened here. Let's say this is a solid wood, and this is also a solid steel, solid. And put this, if I touch it like that, nothing happened, this is bearing, yes or no? Which we are talking about this area or this area, right? Let's say now I have a machine here and ramp this through this and come from the other side out. I'm trying to make a hole here. Everybody's understanding. Okay, this comes out. Yes? What happened here? Which material being damaged? The steel or the wood? Wood. This is what it came out. Yes? Okay. What area being damaged? That area. Was it in the normal state of stress or shear stress? Shear. It was shear off. Everybody see that? We call this one punching shear, please. Many people have problem until I show you this. When I show you this, you should have no problem with it. Is that understood? Many years I was doing this without that, and half of people still was confused about shear. I said, okay, let's make a sample of that and show you. This is exactly where it's going to be. Look what this connection is. Everybody see that? As if you are taking a saw and sawing it like that, like this. Yes? That's what exactly happened. So the area is what? This punching shear, please write it down, which is the same shear as before. This is tau. We call it tau. You just give it a different name because it acts differently. So the tau punching, I hope you can see it from the other side. I'll put it here. Tau punching will be equal to, again, the force. That what my question is, what's the area now? What area are we talking about? We are talking about outside area of this cylinder or inside area of this, which is the same. Is that correct? So what do I need to know to calculate this? I need to know the thickness. The more thicker it is, the more force I need to punch it through. Is that correct or not? And what area? Of course, this is pi times, I need this circumference. Is that correct? Pi times d, which is this circumference, multiplied by t. That's the area. Yes? So therefore, that is equal to pi times d, d being the diameter of this hole, again as usual, which define this circumference, multiplied by thickness t, which define how much area I have here being on. This is also so aside from normal shear stress, normal stress and shear stress, we have a bearing and we have a punching, and that's it. There is nothing else to talk about. Is that understood? Yes? How much time do we have right on time? Yes? Or we have 15 more minutes? 15 more minutes. Okay, good. So let's talk about another problem. Good. So Let's move on. So the next problem we want to talk about is the following. So I'm going to put this up there. I don't think we need that anymore, in case we need it. This time, I'm going to give you a couple of more information, and we go from there. First of all, now, let's go back again, give you another idea here, which is important. Let's say we put here a P here, you put here a P there, you make a cut there. This is under normal stress. When you calculate sigma equal to plus n over the area, we call this sigma applied. Yes or no? This is how much. I give you the P, I give you the area. You can come with some number as we come 200 psi, 300 psi, whatever. So many Pascal, etc. However, if you increase the P and keep increasing it, suddenly this item is going to break. At that point, for time being, let's say that we have a sigma. We call it sigma ultimate. Sigma ultimate is where the item is going to break when it reaches to its limit. Of course, there is more discussion coming in chapter 2. There is not that simple. We talk about for timing. Let's say sigma ultimate is the highest value of sigma I can put in that structure, whatever that is. Is that correct or not? Obviously, you are not going to load this structure to this limit. Everybody understand? You are going to be a difference between the two. The difference between the two is your factor of safety. Everybody knows that. So your factor of safety, define your factor of safety, will be equal to sigma ultimate over sigma applied. So some of your homework, they ask you to calculate factor of safety. Of course, they are going to give you sigma ultimate. You are going to calculate your own sigma applied there. Sometimes they give you in reverse. So sometimes they give you sigma allowed. Sigma allowed is they give you in advance. They take the sigma ultimate and they divide that already by factor of safety. For example, we have a steel, and the steel has 36,000 psi limit to go. The sigma yield, but I'm calling it sigma ultimate at this time. So, and let's say I'm going to use a factor of safety of 3. Therefore, sigma allowed is 12,000 psi. Everybody understand that? Sometimes the problem starts at that. Based on that, you can go back and calculate your value of n, how much load I can put on this object in order to reach to this value, because that's the highest value of gas. So look at your homework. The homework can go one way or another. So that depends on the data that is given. You will calculate that. That will be given to you. Saying it all of that, let's look at this simple problem. Let's see whether we can get all of the information here. Here is the column. It's not in your handout, so you want to write it down. This is a circular column with a diameter of 4 inches. And we have put here 160 kips. By the way, kips is 160,000 pounds. I mean, kips is 1,000 pounds, or here we put 160,000 pounds on the, which is made of steel. This is steel. And this is also steel. But this is still is 10 by 10 inches. And there we put it on the concrete. This is a simple example which shows you everything I talk about today. Okay. Notice sigma allowable in a steel given equal to 18 KSI. Tau allowable in a steel given 9 KSI. Sigma allowable in concrete is given equal to 3,000 PSI. And tau allowable in concrete is given equal to 1,000 PSI. check to see whether anywhere in this material you are okay or not. And let's assume the thickness of this plate is also 1 inch, and the thickness of the concrete is 8 inch, and the size of it is square. Remember, this is what I was talking earlier about. So if you have a column, a steel column, and there is lots of load on it, you cannot put it on the soil. Why? Because the soil has a lower bearing. Everybody knows. Some of you civil engineers may have taken your soil classes. I don't know yet or not. But nevertheless, that you have to put it on a concrete foundation. Every house has a concrete foundation for that reason. Depends how strong the soil underneath is. We have different type of soil too. Is that understood? Yes? Here we put steel, then we put the steel plate there too, also because we want to distribute the load a little bit in the larger area because we are afraid of the punching. So therefore, what's the stress in the column? Let's calculate one by one from top. Let's start from top and go down, see what happened. Everything that I said there, happening there. Punching happening there, bearing happening there, normal stress, shear stress happening there, all of that. Everybody see what I'm talking about, yes? This is a little stress. That's why you have to work with your homework yourself in order to do that discovery. That discovery is engineering part. If you go to the solution manual and they tell you what to do, what you are doing acting like a calculator. That has only 5 points out of 900 points. Everybody for each homework or each quizzes. Remember that, yes? The discovery part, the engineering part is the one you are getting credit for, and you are learning the material. So don't go to ask somebody to how do I do this problem. They tell you to how to do that problem. That problem is done, finished. Go to another problem, do it yourself. Everybody, this is the technique. That is the key to becoming successful in this, not in this class. I don't care about you getting A or B or C. That's your job. However, you want to become a good engineer, that's what you should do in every class, especially in the fundamental classes, dynamic, static, etc., etc. Yes? Strength. Now, what is sigma in the, first of all, the column is under tension or compression. It is under compression. It's very simple. Let's do it. 160,000 pounds divided by pi times 2 square, because that's the area of the column. So I look at the number, 12,739 psi, which is 12.7 or equal to 12.7 KSI. Remember, from a static, we always limit our final analysis to 3 digits. Remember that idea? Some of you are you're using it, some of you not. So I'm reducing that. And then this is less than 18 KSI, so I'm okay. Because this was the limit for still was. So I'm still not to the limit that I can put more load if I want to. Yes or no? Correct? Then what do I need to calculate next? Next, I need to calculate the bearing. But do I need to calculate bearing between the steel and the steel? That's the same thing. That's 12.7. So I don't need to carry that because that's the same material. But do I need to carry the bearing between steel and the concrete? So what area are we talking about? Look at the picture. What area is the steel connection, your contact between the plate and the concrete is 10 by 10. So the load being distributed. In other words, if I show the concrete, I don't have to do that. Everybody see what I'm talking. You have here a uniformly pressure putting on the concrete on the area of 10 by 10. Is that understood? Yes. So sigma bearing on the concrete is equal to, again, 160,000 and divided by 10 by 10. So it is 1,600 psi, and that's less than 3,000 psi. So I'm okay there. Yes or no? So what should I worry about? Is the possibility that column to punch through the plate and go down? Is this possible? Yes. So therefore, assuming the concrete doesn't show any resistance, which does a little bit, Let's assume concrete is not there. So then there is a possibility that this column can punch through here, go through that, yes or no? So let's calculate that punching shear in the plate, assuming concrete has no resistance. Remember, there is some, for factor of safety, we are going to eliminate that, but concrete has some resistance against that. Is that understood? Yes? So as long as it tries to go down and goes halfway down, we are done. Everybody understand that. So the damage is done already. It doesn't have to go all the way down. Is that correct or not? So how much shear? Tau do we have there? Tau in the steel plate. These are what I'm saying, that this is what you have to work on this until you get good at all your homework, that you have to discover it yourself. So will be force again the same, 160,000 pound divided by what area now? This is your homework. There are a couple of homework related to this, so you'll be careful about the punching. So I need, again, this, yes or no? Yeah, that's what in this plate, correct? It's exactly, looks the same size. Okay, so therefore I need this area, right? So the area is pi times what? Pi times diameter, yes, that's right. So it is pi times 4 times thickness of the plate. Thickness of the plate is this much, yes or no? It is 1 inch. So you see, all of them are there. It's just for you to come up with this number. So you look at all the quizzes, you look all the homework, they are now look the same. If you understood this, everything is there. Yes? What? No, we are talking about punching now. We are talking about this upper rod goes through here, cut this one down. Here, punching. Okay? We are not talking, the square came out here as the square because that's what the bearing. This is 10 inch by 10 inch. So it's what's like this. At the middle of the plate, you have like this. This is 10 by 10, and that's the bearing area. Is that understood? Yes? I'll show you a different technique. Anyhow, you calculate that one. So because we are running out of time, let's finish this one. You calculate that one. That become equal to 12,739 psi. But this is larger than tau allowable. Tau allowable is how much? Look, that's larger. So that one is larger than 1,000 psi. Therefore, it's not good. So what should I do? What's the easiest way? And maybe I want to change the thickness of the plate. Actually, the first easiest way. Yeah, you can do that. But remember, if you do that, your column changes. You see, the column is main job. Yes, you design the column, then you design the plate. So design, that is major part. The plate is a small part. So the best thing to do is change the thickness of the plate to the, let's say, 1.5 or 1.8 or 2 inches. Yes?
Isn't the tau allowable for the steel plate 9,000 psi?
Did I say 10,000? Yeah, yeah, this is 12,000. Anyhow, yes, still is larger than 10,000.
Wait, is that 10 or 9?
10,000. This is for this plate, and that is all of them wrong. You're right, 9,000. Larger than, I should look at my note. 9,000 psi was the tau limit for steel. That's right. I went up one down because we have a punching in the concrete too. Is there a punching possibility? I'll let you go in a minute. Is there a punching possibility on the concrete as well? Yes. This plate can go down here. Since we are out of time, I'll let you go. I think we are out of time. I don't want to keep you any longer. Yes. So we have 1 more minute. So that's what we can do that also. Yes.
Didn't you write that it's 9? Oh, no. I didn't
No, I use this as a my tau allowable. We were in the still, that's what he pointed out. They still had 9,000 KSI, but I put 9,000 PSI or 9 KSI, which is the same thing. 9,000 PSI, which is 9 KSI. Sorry for that. But this is still is larger, so therefore it's not good. So I have to do something about it. To do something about it, as she said, you can make the larger hole, but that means you have to use the larger column. I said that's not a good solution, so it's better to change the thickness, a little bit higher thickness. That's it. So next time we are going to continue with the discussion, and then please you are ready now to do all your homework. There is nothing new there except I'm going to do another 1 or 2 examples next time. Okay? All right.